So in this video, we're going to be discussing Cardano's formula and how we can use it to write out a Python function that's going to be able to calculate specific volumes when we're given pressure and temperature. We'll again be using the SRK equation of state. We've already come up with our cubic polynomial, if you remember, for the compressibility factor, where we had the long equation with a bunch of variables. We came up with our A, B, C, and D values for the coefficients. So we're going to be using Cardano's formula to find the roots of that function. And our cubic equation here that we have on the screen just gives us A, B, and C as the coefficients, where we had A through D. But that's going to be okay because our Z cubed was our only variable, only had a coefficient of 1, so we can pretty much ignore that. It'll be alright. So we're going to be using B, C, and D from our derivation as a substitute for their A, B, and C to compute our roots. So in an earlier video, we talked about how the cubic polynomial would be able to help us derive specific volumes of a substance, and that's exactly what we're going to be doing now. So we'll be able to use our coefficients A, B, and C to create a function in Python to give us the specific volume. If we look at our root equations down here, we see that there's some with imaginary numbers, but we're not going to really worry about that or focus on that because remember, we're just focusing at the critical point. In our past videos, we've just talked about everything at the critical point. So that's going to be our one equation here, just focusing on that one root. That's going to be because anywhere above the critical point, we will have one specific volume, and that's because liquid and vapor phases are indistinguishable past our critical point. So since we're going to be using the same substance, water, from our last video, I'm going to use it, just write our code in the same Python collaboratory notebook here. So we can go ahead and begin by writing a function that's going to compute our roots from our A, B, and C values. So we want to define our function. We'll call it cubic roots. And our parameters are going to be A, B, and C. So it says here, with real or complex coefficients A, B, and C, first compute Q and R. So we can go ahead and do that. Alright, so now that we have our equations for Q and R, we can go ahead and look down here. It says if Q and R are real, then and R squared is less than Q cubed, then the cubic equation has 3 roots. So first we need to compute what theta is. So we can go ahead and plug in the equation here. Say theta equals, we're going to need to use numerical Python, which is NP of arc cosine times of r divided by, and the square root of q cubed is going to be the same as 3/2. So we can just say q to the 1.5 power. And this is going to be only if, so we can make an if loop, q and r are real, and r squared is less than q cubed. So we're going to need to indent that also. So now if we scroll down here, we see our 3 roots, which is what we're going to be trying to compute. So if you see in all of these roots, we have a -2 radical q and a minus a over 3. So there's a way we can actually just compute the cosine of our interior bounds here as an array with our theta value, and keep all of this other gunk on the outside so we don't have to keep retyping it every time. So we can go ahead and go ahead and make an expression for our roots. Just say roots are equal to, and they're all going to have the -2 times r q to the 1/2 power times the cosine. So to make an array, we're just going to use these brackets and include each interior value of these cosines. Speed. Okay, so now that we have our equation set up for calculating the roots, we want to make a return statement. And what we're going to want to return is the roots. But Python is just going to return the roots in a random order. We need to specify the order we want the roots to be returned in, because so that our first value, our lowest value, is going to represent the specific volume and the liquid phase, and our intermediate, like in between value, is going to represent obviously somewhere in between, and then our highest value is going to be in our gaseous phase. So to do this, it's actually really simple. Python has a cool tool that we can use. It's just numerical Python sort of our roots. So now that we have our if statement, if r squared is less than q cubed, we also need to have something to state about if that if statement is not true. So we can just say else, because in this case it's just otherwise. So if we look at our equation sheet over here of the Cardano's equations, we see otherwise we're supposed to compute an A equation for A here, where the sign of the square root is chosen to make this greater than or equal to 0. If we look down a little further, saying if Q and R are both real, equations are equivalent to the negative sign R. So that basically this negative sign R is just telling us that it's going to output either 1 or -1. So it's just going to be telling us if our value is positive or negative. So if, for example, if you were to input a positive number, it would output 1. If we were to input a negative number, it would output -1. So we can go ahead and write up our equation for A here. So I'm just starting with everything to the 1/3 power, just so we don't forget that. Include that here. Yeah. So, Alright, so that's our equation for A. So our next step here, come down a little bit. After we find our A value, it's telling us to compute our B. So here our B is going to be reliant on A. So it's saying B is going to equal Q over A. If A is not 0, B is going to equal 0 if A is 0. So we can kind of combine this into one equation just to make it a little simpler. So we can say B is equal to 0 if A is equal to 0. And notice here I'm using two equal signs because it's not an assignment, it is a condition that we need to use in our if statement. So that's telling Python that only if A is equal to 0. And then we can say else, since that's our only condition. Everything else that anytime A is not 0, we're going to have Q divided by A. So now the thing we're trying to return is the root here of our x1, A plus B minus A over 3. And again, we're just going to not really worry about our imaginary numbers right now. So for our return, instead of writing x1, I'm just going to write the equation. So we have A plus B minus little a over 3. So now it looks like we are ready to take our cubic roots A, B, and C to find our cubic specific volume. So we're going to start out by defining this for our function and call it cubic V of temperature and pressure, because those are the temperature and pressure we're going to already know and can import those. So we are going to want our AB I'm sorry. So if you remember from up here, we have, we found our AB, epsilon, and sigma variables, coefficients. So we're going to want to import our cubic coefficients that are reliant on temperature into our function. So we can unpack that and say A, B, epsilon, and sigma are going to be equal to our cubic coefficients, because we're going to be using that in our equations, using those coefficients. So next, I'm going to start with our return, because it just makes it easier if we go ahead and define what we're returning, so that way we can work backwards and get a better understanding of what we're going to need to input in our function. So obviously we're returning our specific volume, and I pulled up the equations and everything that we did a couple videos ago where we found our A, B, C, and D values. So up here we have this equation that says V equals R times Z, T times Z divided by P. So we can go ahead and plug in that equation. So now we can see we're going to want, so we know our R value, temperature, and pressure, but the Z is undefined here, so we know we're going to need Z. We also know we're going to need this beta here and Q, which we used in our coefficients. So we're going to need to go ahead and define the equations for those, so that way we can use those variables when we're making our expressions for A, B, and C. So if we come back up here, we have beta equals V times pressure over R times temperature. So we'll go ahead and type that in. And then Q is going to equal our A over B times R times T. So we'll call Q. And now for our Z was our cubic polynomial, if you remember. So what we can actually do, we found our cubic roots up here, so we are just going to be using that again. So cubic roots. And instead of our A, B, and C that we have up here, we have our expressions for A, B, and C. So we can go ahead and put those in as our A, B, and C values. Alright, so our Z cubic roots look good, and we can go ahead and test this by doing our cubic V and inputting a temperature and pressure. So if we look up at our chart up here, we can actually pick values that are going to be realistic. So I'm going to do 1 e to the 7th and temperature of 600 and see what we get here. So we have 3 values here, which is correct. That's how many values we want for our specific volume, but I believe these volumes are incorrect. So I'm going to look up here and see. We must have something wrong in our cubic roots function up here. I see. Okay, so if we go back to our equation sheet for the Cardano's equation, it looks like I put in this A expression in our else statement, where it should be this A statement. A expression here. So I'm going to change that. So I think I'm just going to go up here and do run all to make sure it gets everything. We come down here. Still are the same values. Alright, so I'm going to take some time and figure out what is incorrect in my code here and come back. So I was able to get it to not be those incorrect 3 values, but, and I believe it was some error in my cubic roots function here. So I retyped that and made it correct, but now it's giving us one answer, and I spent a few hours trying to figure out why it's only giving us one answer instead of 3, because we want it to output 3 specific volumes. So I'm just going to go ahead and explain like what those volumes are going to represent. And hopefully at some point I can figure out what my issue is here. So we should get 3 specific volumes. The first volume in the array would be our lowest volume, and the middle volume is that intermediate volume that we don't really care about because it's an artificial volume and there's not going to be water existing as a liquid or a vapor in that specific volume. And then the third volume would be our water in a gas phase. So we can kind of explain this looking up at our graph that we made up here in the last video. So that first volume that we got should fall along this side. So if we zoom in, we can see if we look at like a straight line along our curves, we can see that there's a point where let's look at this pink one, for example. We'll get rid of these other ones around it. So we can see if we were to make like a straight line at this negative 50 million here, there's going to be a point where it crosses volume in 2 places. So those are the 2 volumes that we are going to be looking at, that lower bound and the upper bound. Those are the 2 volumes that we're trying to get at. So hopefully by doing this, even though I couldn't get the 3 volumes, it can kind of help you understand the Cardano's equation and how we can use that with our cubic polynomial to find those specific volumes for any temperature on a volume pressure chart for water. So after spending some time looking at my code, figuring out what the error was, I realized that I had my temperature and pressure here flopped, and for some reason that was giving us 1 specific volume, and now we have 3 here. So we can see this is our water in liquid phase, this is our water in the gaseous phase, and this intermediate volume here just doesn't really exist. It's just a theoretical volume.